strong base titration. Um, This is the titration curve for strong acid, strong base. And the regions here is just the initial strong acid. This is 0.1 molar hydrochloric, so it has a pH of 1. And then we have excess acid. The excess hydrochloric acid keeps the pH low until we get close to the equivalence point. When we get to the equivalence point, we've neutralized all the acid and we form sodium chloride and water, salt and water. Sodium chloride is a neutral salt, so the pH is 7. And then we go into the excess strong base region here. The pH is going to climb rapidly. The base in this case is sodium hydroxide. If this were just 0.100 molar sodium hydroxide, the pOH would be 1 and the pH would be 13. So this pH is going to slowly climb up and climb up towards 13. We'll never quite get there, but we'll just continue up towards it. It flattens out because we have solution dilution happening as well as the pH going up. Did I talk about the indicators here? Actually, any of these indicators on the vertical part, this is a very steep and long rise. We start off at about a pH of 2. We end up at about a pH of 12. So this is 10 pH units. 10 pH units is 10 orders of magnitude, or 10 powers of 10. This is 10 billion times change in acidity and basicity over this. So there's a huge jump here in going from excess strong acid to excess strong base. In this vertical range, even though the color change of the indicator might not be right at the equivalence point, the amount of error is very, very minimal. And so I talked about bromethymol blue, I think. Did I talk about these indicators? Yeah? Yeah, pretty much. Yeah, you're looking at this happening within a drop, couple of drops, basically. And so it would lead to very slight error. So we just use phenolphthalein. Phenolphthalein is easy because you go from colorless to color. And that's easy to detect, but you can see it's off a little bit because the pH is around 9 here where it starts to change color. When we go to a weak acid, strong base, the weak acid is going to start off at a higher pH. So rather than starting off at 1, we start off at about 3 in this case. The final pH is going to be around the same. You know, we go up to around 12 here, which is excess strong base. But you can see the rise is going to happen between about 5 and 12, which is about 7 pH units here. You know, and the real vertical part happens over like 3 or 4 pH units. And so this is going to limit the choices of indicator, but one indicator that works really well for this is phenolphthalein. And so in this titration, we're titrating acetic acid with sodium hydroxide, which forms sodium acetate. So the salt here is sodium acetate and water. The salt is basic, so that's why the pH is above 7 here. So this is it. So one of the pHs that we calculated was at the equivalence point. So this takes 25 milliliters to reach the equivalence point because we're titrating 25 milliliters of acid at 0.100 molar. And if the base is the same, 0.100 molar, we're going to need the same volume, 25 milliliters. So we'll have both. Here. At the half equivalence point, which will be at 12.5 milliliters, we did the calculation, correct? But you don't have to do the calculation. When we have this type of titration, you should know that the pH is equal to pKa at the half equivalence point. We have a weak acid, strong base. And so You could do the calculation, but it's not absolutely necessary to do. And so this type of question on a test would, you could just write the answer here. But we could have other points along here that we need to know what the pH is. And so, for example, we might not be at the half equivalence point. There are other points that we could be at. We could be at the 1/4 equivalence point. So half equivalence point occurs at 12.5. The 1/4 equivalence point occurs at 6.25 milliliters. Or we could be at the 3/4 equivalence point. 3/4 of the way to 25 would be 18.75 milliliters, about here, 3/4. Or some other distance between 0 and 25. 25 being the equivalence point here. So let's do some more calculations. All the calculations follow the same kind of format that we just did. In fact, all the calculations on the titration curve, we can do the same type of setup. And so the next one is we're going to do it at the 1/4 equivalence point. Which would be 6.25 milliliters. So let's go ahead and do that. So we're taking our original 25 milliliters, so we start the problem over again. Even though we already did the half equivalence point, we're not going to use that at all. And so we're taking our original 25 milliliters of acid. I did 3 sig figs, but I'll change this to 4 since we're going 2 decimal places here. So we have 25.00 milliliters of acid, since I don't want to round this. And then what we end up with here at the end of this titration is a total volume of 31.25. This is 6.25 milliliters of sodium hydroxide solution. And that's going to give us a total of 31.25 milliliters of mixture. And so this is the reaction mixture before we let it react. And so we're going to have to calculate the concentrations, initial concentrations of the reaction mixture. And so we'll do the solution dilution. So the acid is going to be 25.00 over 31.25 times 0.100 molar. And so let's go ahead and calculate what that comes out to. 25 divided by 31.25 times 0.1. And so we had 0.08 hundredth, or 8,000 molar. And then we'll calculate the initial concentration of the sodium hydroxide after solution dilution. This is going to be 6.25 over 31.25 dilution, 0.100 molar. And this comes out to 0.0200 molar. All right, that's our step I, the solution dilution. And then we go to step 1. Step 1 in titrations is the strongest acid, in this case acetic acid, plus the strongest base, which would be sodium hydroxide. And this is going to form the salt, sodium acetate, and water. The initial concentration after solution dilution of the acetic acid is 0.0800. And the initial concentration of sodium hydroxide after solution dilution is going to be 0.0200. And the sodium acetate will be 0. Water is a pure liquid. Okay, now we're in the excess acid region, but this excess acid region for a weak acid and a strong base is called the buffer region. And so we aren't going to neutralize all our acids. The limiting reagent here is the sodium hydroxide, and so we're going to lose all that. And so we're going to end up with 0.0600, 0, and 0.0200. So this mixture here at the end is a HAC and NaAC mixture. And so the type of mixture is a weak acid and its conjugate base. And so we have a weak acid, weak base pair that are conjugates. When we have a weak acid, weak base pair that are conjugates, this is an HH buffer. And so in step 2, we aren't going to do the ice table. If we have an HH buffer, we could just use the HH equation. So we did it at the 1/4 equivalence point. We did step I, and then step 1, and then step 2, which is the Henderson-Hasselbalch. When we're in the buffer region, I'll show you this shortcut that we can do. The buffer region. So we need to know the equivalence point. It's 25 milliliters. The half equivalence point, 12.5 milliliters. And the 1/4 equivalence point, 6.25 milliliters. And this is the 1/4, the 1/2. This would be the equivalence point, the full equivalence point, number 1. And so if we know we're at the 1/4 equivalence point, then what that means is we haven't added enough base to neutralize all the acid. We've only added enough base to neutralize 1/4, because we're only 1/4 of the way to 25. And so we've neutralized 1/4 of the acid, original acid. 1/4 of original acid. And so what the shortcut is we go straight to the Henderson-Hasselbalch equation. The pH is equal to pKa plus the log of the sodium acetate or acetate over the acetic acid. And this is going to equal the pKa plus the log. Okay, what happens is the sodium acetate is the product of neutralization here. So however much I've neutralized, I've only neutralized 200, 0.02 worth of acid. And that gives me 0.02 base, and that leaves me with 0.06. So out of the 0.08 that was here originally, I've neutralized 0.02 worth, 1/4 of it. So rather than putting these numbers in here, this is 1/4. You see that? This is 1/4 left over of the original 800. And over here, this is 3/4 of the original 800. And so I'm just going to put the fractions in here. The amount of base I I produce is 1/4. The amount of unreacted acid I have left over is 3/4. So this is the 1/4 equivalence point here. Meaning I've neutralized 1/4 of my acid, and this is how much acid I have left over. 3/4 of the acid left over, unreacted. And so this is my 3/4 that's left over, unreacted. This is my 1/4 that's reacted here, out of the 0.0800 original. And so what this equals here is, this equals pKa plus the log of, okay, 1/4 divided by 3/4 is equal to what? 1/3. So it's a log of 1/3. And so I get pKa minus 0.477. So let's try another example of this. The next example will be the 3/4 equivalence point. So what I'm going to do is, if I'm at the 3/4 equivalence point, how many milliliters is that? We'll have to figure out how many milliliters that is. Actually, let's just take a look at this curve here, because it's a little easier. So at the halfway point, we're at 12.5. And so at the 3/4, it'll be another 6.25 beyond that. So that's 6 and 12 is 18.5 plus a quarter, 1875 milliliters. So at the 3/4 equivalence point, I'm 3/4. In other words, this is 3/4 of 25 milliliters. 3/4 of 25 milliliters is 18.75 milliliters. And so this is plus 18.75 milliliters of sodium hydroxide. Okay, with the shortcut method, I'm not even going to bother doing solution dilution. I don't have to do the solution dilution. Buffer, you know, the pH of buffers doesn't depend on the actual concentration. It just depends on the ratio of the concentrations. As long as you have significant quantities of both present. And so what I'm going to do here is I'm just going to go straight to the Henderson-Hausbach. The pH is equal to the pKa plus the log. Now, how much acid have I neutralized at the 3/4 equivalence point? 3/4. And all that 3/4 that was neutralized is going to turn into base. And so I'll have 3 parts base. And how much is left over? 1/4. 1 part. 3 parts base, 1 part acid. 3/4 of this will be sodium acetate. 1/4 of this will be acetic acid. And so what this is equal to is equal to the pKa plus the log of 3/1. The inverse. And so this is going to equal pKa plus 0.477. And so this allows me to get the pHs quite rapidly. I don't know if I still have my curve. I do. Actually, I do have my curve here. So at the half equivalence point, the pH was 474. It's just the pKa. At the 1/4 equivalence point, it would be 474 minus 0.477. At the 3/4 equivalence point, it would be 1875. It's going to be plus 0.477. So I'll just write that here. I'm going to have pKa minus 0.477. And then over here at the 3/4, it's going to be the pKa plus 0.477. So right now I have 3 points that require barely any calculation if you do the shortcut method. And so here, getting the midway point's easy. That's a pKa 474. Look it up in the book. Get the 1/4 by subtracting about 0.48. Get the 3/4 by adding 0.48. 3 points defining this. But there are 2 more points that are quite convenient. And you might think this, you might think, well, let's do the 1/10 equivalence point. That might be convenient because, 1/10 of 25 milliliters is 2.5 milliliters. So we can get the pH at 2.5 milliliters quite easy. But this one's a bit more of a pain. There's an easier one than this. I don't like the 1/10. Even though the number looks pretty good. You know what I like? I like the 1/11th equivalence point. Now that seems like an odd number, 1/11th. What is 1/11th of 25 milliliters? And so 1/11th of 25 milliliters will tell me I've only neutralized 1 part out of 11 of 25 milliliters, or 1/11th of 25, which is going to be a weird number. And so that's 25 divided by 11, 2.27 milliliters. At 2.272 milliliters, the pH determination is very easy. And so if I'm at the 1/11th, I've only neutralized 1/11th, so I'm going to go straight to the Henderson-Hasselbalch. I'm going to use the shortcut method. And this is going to be pKa plus the log of how much of the acid have I neutralized. I've only neutralized 1/11th out of my 25 milliliters. That means how much do I have left over? I have 10/11ths left over. And so, but if I look at this, this is going to be pKa plus the log of 1/10. Or 10 to the minus 1. Well, if it's the log of 10 to the minus 1, then we bring the minus 1 in front, and this becomes pKa minus 1. So this is a very rapid point to get. So at 1/11th of 25 milliliters, I can get the pH quite easily. Because at 1/11th of 25 milliliters is 2.27 milliliters. It's kind of an odd number, but at 2.27 milliliters, the pH is 374. The pH is 374 because that's pKa minus 1. And there's another point I can get quite easily. And what is that? Yeah, at the 10/11ths. At the 10/11ths equivalence point, the volume is going to be kind of weird because that means we've neutralized, or we've gone 10/11ths out of the weight at 25 milliliters. And so what's 10/11ths of 25 milliliters? It's going to be 10 times this, I guess. So it's going to be 22.72 milliliters. At 22.72 milliliters, the pH is very easy. The pH is equal to the pKa plus the log of, okay, I'm going to convert 10/11ths in the product, and that means I only have 1/11th left to neutralize. Yeah, and so this is going to be pKa plus the log of 10, which is going to be pKa plus 1. So at 22.72 milliliters, I'm at pKa plus 1. So here, pKa plus 1 is going to be 474 plus 1 gives me 574. So this is pKa minus 1. And this is pKa plus 1. And so I have 5 points mapping out the buffer region. the pKa plus or minus 0.477, and the pKa plus or minus 1. And so this is pretty well mapped out, the buffer region. Let's take a look on this graph up here. So they give us the pKa here, 474, right there. So I'll do 1/11 of 25, which is 2.27. And so I'm at 474. 474 minus 1 is 374. So that puts me about here. And then 574 is going to be 3/4, 22.7 here. 574. And we call this a buffer region. In the buffer region, do you see how flat the pH is? Even though I'm adding strong base, the pH stays relatively flat. And that's what defines a buffer. A buffer has a fairly stable pH in spite of strong base. You know, this strong base is very high pH. If you measure the pH of just the base alone, it's pH 13. And yet when we add this in the buffer region, the pH barely changes. It will change at the periphery. So for example, when we get to 574, then you can see the pH starts to increase rapidly. And when we're down at 374, kind of drops more dramatically over here than before. It's really pretty flat between the range of 374 to about 574, and that's about it for the range. Outside of the range, it's kind of what we say a lopsided buffer. And so if we're over here, we have lots of acid, very little base. If we're over here, we have lots of base, that is sodium acetate, but very little acid. And the pH changes more dramatically. So there are a couple of things when we're thinking about buffers. You know, when we want to make a buffer, there are different ways to make a buffer. One way to make a buffer is just take some acetic acid and neutralize it with sodium hydroxide, and then you're going to form the acetic acid acetate buffer. And so one way is we could just add sodium hydroxide until we get to the desired pH. But the best is here, right in the center. Because if we're right in the center, the equivalence point, then we have a 50-50 mix of base to acid. A 50-50, like a 1-to-1 mix of base to acid, gives the most versatile buffer, because we can add acid, it stays fairly flat. We could add base, it stays fairly flat over the widest possible range. And so we call this the optimum pH of the buffer system. And so in this case, the pK is 474, and the pKa is equal to the optimum pH of the buffer system. But that may not be the optimum pH for your buffer. You know, do you really want to use a 474 buffer? You can, you know, but it's more convenient in whole numbers. So for example, a pH 4 buffer would be good. But if we have a pH 4 buffer, then it's more heavily biased towards acid. There. Or we could have a pH 5 buffer. pH 5 buffer might be pretty good. pH 5 buffer would be in this region. Still kind of a mix. But a pH 6 buffer, would a pH 6 buffer be very useful using this system? No, because a pH 6 buffer has way too much base, not enough acid. And so its response isn't going to be so flat. And so what we say is this is the optimum pH here, but we have a usable range. And so the buffer range is between pKa minus 1, 374, and pKa plus 1, 574. So the buffer range is 374 to 574 for this particular system. Uh-huh.
If the sodium hydroxide was twice as strong in molarity, would it reach equivalence point twice as fast?
Yes. Yeah. In your homework, you're going to have different concentrations, and so it throws things off. So if your acid were 0.100 and your base was 0.200, then the equivalence point would have come twice as fast, 12.5 milliliters. And the half equivalence point would have been 6.25. So you have to adjust everything stoichiometrically there. What they also like to do is they like to not have nice, clean numbers like this. So what they might do is they might make the acid like an odd number, 0.113, something like that, and the base 0.189. And that screws everything up because then you have to do a Chem 1A style stoichiometry calculation to figure out how many milliliters you need to neutralize it with the different concentrations. And so it's nice to have numbers like this where you can just do it, the calculation in your head. And that's why I picked 0.100 and 0.100 because then it's just one-to-one volume wise. So basically, we can make a buffer ranging anywhere from pH 374 to 574 using this buffer system. But ideally, something close to 474 would be best. Okay. Go back. Okay, so there are different reasons we might be interested in this range. If we're interested in making a buffer, this is one way of making a buffer. There are other ways of making the buffer as well. But here, if we're looking in the buffer region here, we're forming a buffer in this reaction. The product is a buffer. And so this would be the optimum pH. And then the range would be from pKa minus 1 to pKa plus 1. In between these two limits here, this is called the buffer range. And so optimum pH, buffer range. The buffer range is just for making a practical buffer, but we can be outside the buffer range. And so for the Henderson-Hasselbalch, we can go outside this range here. And so the HH equation can be used over a wider range than this. The HH equation, however, fails when we get very close to the equivalence here and very close to the beginning. In this failure range here, we can't use it. We have to use the ice table. The HH allows us to skip the ice table, but at the extremes, we're going to have to use the ice because this is practically all sodium acetate here, and this is practically all acetic acid here with barely any acetate, and this has barely any acetic acid. In that case, the HH equation fails because the HH equation relies on the simplifying assumption working, and if the concentration of one or the other species is so small, then it's not going to work. It's going to be a more significant change. So what we're going to do in this next calculation is let's make a pH 5 buffer. You know, pH 5 is close to the optimum pH of 474. One is we can just mix acetic acid and sodium acetate together in the right ratio. We can adjust the ratio until the pH hits 5, and that's in our buffer region. If we have a pH meter. If we don't, then we can calculate it, what the right ratio is. You know, using the Henderson-Hasselbalch equation, the pH is equal to pKa plus the log of the ratio of sodium acetate to acetic acid. And we want to set this equal to 5.00. And so we just solve for the correct ratio of base to acid. The other way is we can make it by a reaction. So, for example, we could take acetic acid and react it with sodium hydroxide. And so the acetic acid plus sodium hydroxide, we have to make sure we have excess acetic acid, because a buffer isn't a mixture of weak acid and strong base. We need the strong base to be the limiting reagent because we can't have any left over. And so if the sodium hydroxide is the limiting reagent, then at the end of this we're going to have some HAC, and we're going to have 0 sodium hydroxide, and we're going to have sodium acetate. And so we end up with a mixture. This is an HH buffer. And so essentially we're making it here. And so we just add, keep adding sodium hydroxide until we get to the desired pH. You could do that with a pH meter. Or you could go the opposite direction. You could take sodium acetate and do kind of a reverse titration where we're starting with a base and then adding acid, a strong acid like HCl. And this is going to form acetic acid and sodium acetate mixture. We're also going to get sodium chloride as a product. So this is another alternative here. As long as we have excess sodium acetate in this case, and HCl is a limiting reagent, then we're going to end up with an HH buffer. So what we're going to do is we're not going to use a pH meter. We're going to calculate how many milliliters I need to add.
Can you keep it up longer?
Yeah. In lab, this is the way you made the buffer, right? You took some acetic acid and then you started adding solid sodium acetate to that, remember? and stirred until the pH hit. I think we made a pH 4 buffer at the time. So in this case, we're going to make it by titration. So we're going to make the buffer by titration. And so I'm going to show you the shortcut calculation versus the ice. If we do this with the ice method, we go backwards. Normally, in an ice table, we start at the top and work down. But if we want to do this particular problem, we have to start at the bottom and work our way up. They'll tell us how much. But what I'm going to do is I'm just going to look at the shortcut method here. So we have the pH. The desired pH is 5.00. This is what we want. This is equal to pKa plus the log of the base to acid. Which is equal to 4.74 for this particular system. Other acids have different pKa's, plus the log of this ratio. And so subtract 474 from both sides, I'm going to get 0.26. This is equal to the log of the ratio. And then solve for the ratio here. And so the sodium acetate to acetic acid ratio is 10 to the 0.26, which is equal to 181.9. And so it's a 181.9 to 1 ratio. Now how many sig figs am I allowed? This is 2 sig figs here. So I'm only allowed 2 sig figs here, so it's a 1.8 to 1 ratio, but I'm going to carry a couple of extra to minimize round off error. And so what does this say? This says that I need 1.819 parts or molarity of sodium acetate for every 1.00 molar acetic acid. But how can I get that ratio? In this titration, how many milliliters of sodium hydroxide will it take to read this ratio? And so what I'm going to do is I'm going to rearrange it. This is 1.819 parts of product. And so it's 1.819 parts of product out of a total of 2.819. Where did the 2.819 come from? That comes from this. Because I'm going to have 1.00 parts out of 2.819 parts of unreacted acid. And so where this 2.819 comes from is this. It's just 1.00 plus 1.819 gives me the total parts. And this first fraction on the top is what we call the equivalence point. In other words, how can I get this ratio here? And how I can get that ratio is this. I can say that instead of 2.819 total parts, I'm going to do this. I'm going to go 1.819 out of 2.819 is going to be the same thing as X milliliters out of 25.00 milliliters total. And so how many milliliters would I have to neutralize out of the 25 to get the same ratio? In other words, X is just going to equal the fraction 1819 over 2819 times 25. And that's 16.131 milliliters. And so on this titration curve, bring up the titration curve here. I'm going to hit pH 5.00 here at 16.13 milliliters. So 16.13 milliliters, I'll hit pH 5. And so that's a calculation where we go from the pH to the volume. And then we did a number of calculations where we go from the volume to the pH. And so it's going both ways here. Okay, there's some more buffer terms that you need to get familiar with. You know, this is how we can make it in this particular titration. We need this amount to get this fraction. This gives us another way of making it, though. This is the base to acid ratio. The base to acid ratio, this is for conjugates. They both have to be weak. You can't put a strong base here, up here. If you put sodium hydroxide up here, it doesn't work. And they have to be conjugates of one another. Then it works. But this brings up another term that you should know. You should know optimum pH, you should know buffer range, and you should know buffer capacity. One of the things is this is going to be a fairly low capacity buffer, because what's going to happen is we started off with 0.1 molar, and then we're going to get this ratio here. In fact, we started off with less than 0.1 molar because of solution dilution. And so this buffer is going to have fairly low capacity. And so another way of thinking about buffers and making buffers is we have a 1.819 to 1, I'll just say 1.00 ratio that we have to maintain. And so we might try to do a high capacity. Let's go with 181.9 molar sodium acetate and 100.0 molar acetic acid. And so we have a 181.9 to 100 ratio. Well, that's the same ratio as this. When we plug this into the Henderson-Hasselbalch, this is going to give us the correct pH. So this is going to be pH 5.00. But you take a look at those concentrations. This is very high capacity because there's lots of base and lots of acid in this buffer, but not feasible. It's not feasible because of the concentrations probably exceed the solubility. can you really dissolve 200 moles of sodium acetate in a liter? Maybe, maybe not. And so I should put a little asterisk here. But one thing for sure is this is going to be a highly concentrated buffer. Highly concentrated. A highly concentrated buffer like that is going to be very expensive. So we could go to the opposite extreme. Let's go 0.000001819. So I don't need a decimal there. Over 0.000000100 sub-zero. And so we have the same ratio. This is going to give us the same pH, these two buffers. But this is a very low capacity. And we have to start worrying about dilution. Ultimately, if you keep diluting it, the pH is going to approach what? 7. Because it's going to be so weak, it's going to be almost like pure water. It's going to lose its buffering ability. And so this is very low capacity. It's not going to take much, extra sodium hydroxide to cause the pH to skyrocket, or extra strong base. And so we have a capacity of 1819 molar to 1. This is a decent capacity buffer. I mean, I have almost 2 molar base and 1 molar acid. This is biased towards base because the pH is a little higher. Rather than 474, it's 500. And so we have to worry about buffer capacity. The higher the capacity, the more stable the pH is. The lower the capacity, the less stable the pH is. The pH is prone to wide swings. Because what you can do is you can easily knock out the tiny bit of acid you have in here. This is 1/10 of a micromolar acid. 1/10 of a micromolar is not going to take very many moles of base to completely eliminate that. What we have in this particular problem is something between these two here in terms of capacity. And capacity is the ability to neutralize added acids and added bases to stay stable in terms of pH. Okay, any questions on this? No? All right, let's do a couple more calculations. So we can knock out these calculations in the buffer region quite rapidly. And so these, if I wanted to generate a titration curve, I can get these points fast. pKa minus 1, it's a 1/11th equivalence point, so 1/11th of whatever the total is. pKa minus 0.477, the 1/4 equivalence point, so 1/4 of the total. The 1/2, pH is equal to pKa, 1/2 of the total. 3/4, 10/11ths, those are rapid. Okay, the next point we're going to do is the equivalence point. The equivalence point is going to be the salt. But in this case, the salt is basic. And so we'll have the basic salt and water. And so let's go ahead and do that. So at the equivalence point, we're going to add plus 25.00 milliliters of sodium hydroxide, NaOH. And so the total mixture volume is going to be 50.00 milliliters. And then let's do the solution dilution. The acetic acid is going to be at 25 to 50 to, I'll just do 4 sig figs, a 0.100 molar. And so we're going to get 0.0500 molar. Just carry an extra digit. And then the sodium hydroxide is going to be the same. It's going to be at 25 to 50 dilution of 0.100 molar. So I'm just going to go straight to concentration. It should be the same, 0.0500 sub-0 molar. Okay, once we figure out the initial concentrations of the reaction mixture, then we'll react it. And so HAC plus NaOH is going to give us NaAC plus water. And so the initial is 0.0500 and 0.0500. The change is going to be complete. This is stoichiometric. This is at the equivalence point, so we have equal amounts of acid and base, and so they're going to neutralize each other out, since K is very, very large for this. And then the sodium acetate gains 0.500, and that leaves us with 0.500 molar here. Oh, 500, thanks. So we're left with a basic salt here. And so what's the strongest acid present? Well, acetate will be the strongest base present. The strongest acid present will be
Can you go back up? Sorry.
there's no more acetic acid left over. Neutralized all of it. There's no more sodium hydroxide left over. Neutralize that. We just have sodium acetate. Sodium ions are neutral, but acetate is a base, and the strongest acid that's present is water. This is Kb, JC. So initially we're going to have 0.0500 molar. Acetate, water is pure liquid. This is 0. This is 0. The change is going to be minus X molar because of the Kb. The Kb for acetate is equal to, well, it's not in the chart, so we'll have to calculate it. It's going to be Kw divided by the Ka for which acid? Acetic acid. This is 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. You don't have to have that memorized. And this is going to equal 5.55 times 10 to the minus 10. So to equilibrium, we're going to put 0.0500 minus X, X, and X. So this will equal the HAC concentration times the OH minus concentration of equilibrium divided by the acetate concentration. And so that's going to give us X times X is X squared divided by 0.0500 minus X. And then we're going to just try the simplifying assumption, see if it works. This is going to give us X squared over 0.0500. And that means X is equal to it's a pretty weak base. So Kb is 5.55 times 10 to the minus 10 times 0.05 equals, and then take the square root of that. Answer. I get 5.26 times 10 to the negative 6. So how much hydroxide I generate is 5.26 times 10 to the minus 6. What else contributes hydroxide? What else contributes hydroxide is Kw. So should we do Kw? Is Kw necessary? Is it going to contribute a significant amount of hydroxide? And the answer is no. We don't. Because the most Kw can contribute is 10 to the minus 7 when there's no common ion. But since we have common ion in here already, it's going to contribute a lot less. And so I wouldn't worry about Kw unless the hydroxide were down, lower, like 10 to the minus 8, 10 to the minus 9, and below, I'd worry about it. At 10 to the minus 7, I probably wouldn't worry about it because the common ion effect would. Probably still not be significant. And so Kw, no. The contribution is going to be quite small. 1, Kw is 10 to the minus 14. 2, we have common ion. Okay, so if that's the case, then I'm going to go ahead and calculate the pOH. The pOH is the negative log of the OH minus concentration, which would be 5.26 times 10 minus 6. And so the pOH comes out to 5.278. And therefore the pH is 14 minus that, which is 8.72. 1. So at the equivalence point, we have sodium acetate. That sodium acetate salt is expected to have a pH of 8.72. Here, 8.72, right at that black dot. It's the equivalence point. And it just consists of sodium acetate and water. Now, if we continue adding sodium hydroxide, there's no more acid to neutralize. And so that's just going to add to the total hydroxide, and the pH skyrockets there. And so let's take a look at another calculation here. We're going to add one more drop past the equivalence point. And so the next example is we're going to add 25 point, okay, one drop is about how many milliliters, you know? Yeah, about 0.05. About 20 drops per mil. And so we're going to go one drop. If we go one drop past the equivalence point, do you see, look what happens to the pH, it kind of skyrockets up here. And so with one drop past, we're probably up here now. So let's go ahead and calculate what the pH is going to be. And so let's say you overshot your titration by one drop. Where is the pH now? If you were trying for the equivalence point. And so the total reaction mixture is going to be 25 plus 25.05, which is going to give us 50.05 milliliters. And then let's go ahead and start over with the acetic acid. This is going to be a 25 to 50.05 solution of 0.100. And the sodium hydroxide is going to be a 25.05 to 50.05 dilution of 0.100.
How did you get the 50.05 milliliters?
50.05 is the total.
Is
So,
that what oh, it's half.
because I didn't write the 25 milliliters of acid here. So on the other side of this plus sign is 25.00 milliliters of acetic acid. And so it's just the combined volume, 25 and 25.05, 50.05. So let's go ahead and calculate those numbers. 25 divided by 50.05 times 0.1. 0.04995. I'll just go one more digit. I'm not allowed this many sig figs. I'm allowed 3 sig figs here. Okay, the other dilution is 25.05 over 50.05 times 0.1. Oops. And that gives me 0.0500499 molar. Okay, then what do you do next? So go ahead and we have a few minutes left. Go with the next step here and tell me what that is. I just have to do something really